think I have enough battery. We'll just try it.
Okay.
Whatever I get, I get.
Is it on airplane mode?
It is on airplane mode. Okay, so.
Everyone's covered.
Order!
Nice.
You are the court. You're supposed to be ordering. Order in the court, literally. Order in the homecoming court. Big idea 1, enduring understanding 1D. Who wants to read all about that? Oh. Deborah.
Atoms are so small that they are difficult to study directly. Atomic models are constructed to explain experimental data on collections of atoms.
Cool. Atoms are small. Everybody know that?
Yes.
Right? In fact, we actually could not see atoms, individual atoms, probably until 80s, 90s, something like that. Okay, with the advancement of really, really, really high sensitivity electron microscopes. Better than the one that we're going to see on Wednesday. The one we're going to see on Wednesday is going to blow your mind. It's amazing, but it still can't see individual atoms. Okay, but we've known about atoms for hundreds of years. So how the heck is it that we knew atoms existed before we could see them? Data. Right? What kind of data? That is exactly what we are going to talk about. In fact, what I'm really interested in is the learning target. So yeah, you read the learning target. The learning objectives, sorry.
Given information about a particular model of the atom, the student is able to determine if the model is consistent with specified estimates.
Okay? So I don't know what they're going to do for this. But I know some of the models of the atom that we've had in the past, and I know what evidence supported those models and what evidence contradicted those. So what we're going to do for the next couple of periods is talk about those different models and talk about the evidence that led to that model and then the evidence that overturned that model. And when I say overturned, I'm not talking about like a paradigm shift. Have you guys heard that term before? What's an example of a paradigm shift in science? Sure, like heliocentricity, right? Thinking that the sun is the center of the solar system instead of Earth. That's a whole different way of conceiving of how our stars and planets exist. Okay. So I'm not talking about paradigm shifting, I'm talking about just modifications to these theories. So no theory of the atom completely overturned the other theories, they just made some modifications to it. Okay? This is a really interesting, this is one of my favorite parts of chemistry, even though it's really more history, but it's really cool. I'm kind of fascinated by the history of chemistry, which is why I have some of these super old textbooks. In one of these old textbooks, I think it's this one from 1837, they describe Dalton's theory of the atom as an elegant and probable hypothesis. They say, we will never know for sure whether atoms exist, but we can describe it as an elegant and probable hypothesis. Okay? But all of you are just like, of course there's atoms, right? Because Ms. Bia told us there were atoms, so that proves it. Now, I'm going to prove to you, actually I sort of already did prove to you, I think, that there is evidence for why atoms exist. So we go back to 1808. That's John Dalton. In 1808, John Dalton came up with the first true modern atomic theory. People have been talking about atoms since the Greeks, Democritus, but they didn't have any evidence. They just said, well, here's what I think. It could be like this. Okay, why did people first believe Dalton and make him the first person that came up with a modern atomic theory? The evidence. And the evidence that we talked about, three main laws. We talked about the law of conservation of matter. We talked about the law of definite proportions and the law of multiple proportions. And really, this is the big one. this is the key one that, to me, makes it pretty unambiguous that there have to be little bits of matter that can't be subdivided. You can't have half an atom of hydrogen, for example. The law of multiple proportions. Anybody remember what that says?
Oh, well, so then we're like, if you hold the mass of one element constant, then like, there's gonna be different masses for different compounds of the other one.
Not exactly. Some of you are going to have to do some reviewing on the law of multiple proportions before the big idea exam in 2 weeks.
Pairs of elements that form. If two elements form more than one compound between them, the ratio of the masses of the second element, which combine the fixed mass of the first element, will be ratios of small and multiple.
Everybody know that?
The only thing that is
Right. Okay. Reading it off of your outline is very different than being able to conceptualize it on an exam. What it says is if two elements form different compounds, that's the same two elements. If we control the mass of one, we make one mass the same in both compounds. Then when we look at the mass of the other element in those two different compounds, those masses will reduce to ratios of small whole numbers. The reason is that compounds are all made of whole number combinations of atoms. All the atoms have different masses, but because they can only combine in certain ratios, when we look at the ratio of those masses, we're always going to reduce them to ratios of small whole numbers. That's the law of multiple proportions. The law of definite proportions also gives us some credibility in saying that if every sample of water is 11.2% hydrogen by mass, it's probably reasonable to believe that there's some smallest unit of water, and combined with this law of multiple proportions, we could say that maybe that's H2O. Right? Although, did I mention that in this book they have the wrong formula of water?
Yeah.
Right? Yes, because they didn't know about the diatomics. So when they measured hydrogen's mass, they measured it twice as big as it should be. So everything else, since all these masses are relative to each other, they had them off. They had some problems, right? They thought it was just HO instead of H2O. Okay? Now, Dalton's atomic theory actually has a couple of points here, and I should link to the Wikipedia page so that you can read all about John Dalton. So that when you guys are taking your prom pictures, I want to bring this back. The whole tucking the hand into the buttons. I think that's a sweet look. I think we should all try to get our portraits. Those of us that have ever worn a shirt with buttons. Interestingly, this guy did a bunch of really cool stuff. Chemist, physicist, meteorologist. He was researched color blindness. Right? Anybody ever here take a colorblind test?
Yeah.
Oh, is anybody colorblind in here?
Apparently. My little brother is. It doesn't count.
Are you really?
No, he's not. He just says he's colorblind.
Who?
Michael.
Michael?
You think?
No, he's not.
I don't think being colorblind's cool.
No.
Yeah, I can't differentiate between red and green. Cool. I mean, it's not cool or not cool.
Most
It's
likely
the
to have a
thing.
colorblind
So,
person that doesn't die.
Can you read the number that's in the circle on the upper right?
Wait, hold on.
5. How about middle right?
3.
Middle left?
15.
If you can't see those numbers that are represented in here, then you have red-green color blindness. You're missing one of those. You're not blind, but you are missing in the cones. In the cones of your eyes, there's 3 different pigments that absorb 3 different colors of light. And so you're missing one of those pigments, which prevents you from differentiating between these different colors. That's not what I really want you to know about John Dalton. Okay, this is what I want you to know about John Dalton. The main points of his theory. Elements are made of extremely small particles called atoms. Again, people have been proposing this for thousands of years. Atoms of a given element are identical in size, mass, and other properties atoms of different elements differ in size, mass, and other properties. Is that true?
Like,
Oh, no, not
because
necessarily.
same
Not
elements
'cause you
have
have
like
isotopes.
different masses, so that's why we have the isotope.
Oh, okay, so different atoms can have different masses, and we call those isotopes. How do you know there's isotopes?
Just
Powerful. Very powerful argument. I'm humbled by your eloquence
Thanks.
and brevity. Michael.
Like with carbon dating and stuff, like you can like identify like how old something is based off of like how much like carbon 14 is.
Yeah, how do you do that?
that?
I don't know, I just know they can do it. So if they can do it, it's gotta be, yeah. So one of the things I really want to talk about today is how do we actually know that there are different masses of the elements?
Wait, so is he wrong on 2 and 3? For sure.
Yes, he was wrong on 3 as well. He said atoms cannot be subdivided, created, or destroyed. There's a reason he thought this. It's the law of conservation of mass, right? What you put into a chemical reaction, you get out of a chemical reaction. So it stands to reason that atoms cannot be destroyed. You can't just create atoms out of nothing, right? But the subdividing thing is actually wrong on a couple of different points that we're going to talk about.
We got a 60%.
Atoms, yeah, 60%, he's passing. Atoms of a different element combine in simple whole number ratios to form chemical compounds. That's true, but also slightly untrue. It depends on your definition of compounds. Sometimes when you look at some of the new exotic materials that they're making, especially ionic substances, where they put a few different little bits of one atom mixed in the crystal lattice of another, you might see fractional subscripts on your chemical formulas. Yeah. Y 1.7. What?
Can we not?
We won't. In chemical reactions, atoms are combined, separated, or rearranged, right? So when we draw pictures of chemical reactions, we're going to be relying on this part 5 and showing atoms as little spheres and showing how they combine and rearrange and things like that. Okay? The one I want to talk about to start with is number 3. Atoms cannot be subdivided, created, or destroyed. I'm going to show you how they can be subdivided using a piece of equipment up here. I'm going to split an atom.
Oh my god.
I'm going to die eventually, but not today.
Not
All right, this device here. Yeah, order. This device right here is commonly referred to as a
Taser.
handheld Tesla coil. It would act like a taser. Or to put it to your skin, it is a high voltage transformer.
Wait, let's see his, wait, look at his hair. Let's try it.
So I can put this close to a piece of metal. This metal is running down into the earth, and so it's providing a path for those electrons to get back to the ground.
Like that.
Okay? Let's test this hard. Interestingly enough, side question. What color is a lightning bolt?
Everything.
If you say yellow, you read too many comic books. If you say blue, you watch too many movies. If you say white, you're partially right because a big enough lightning bolt will have the center of it will be white. However, they always have a hue on the outside, which I just showed you.
Purple?
Purple.
Hey.
I just showed you a lightning bolt, and you're going to tell me lightning bolts are yellow? Yeah, they draw yellow. They draw yellow in the comic books, right? Think about that, like stereotypical lightning bolt. That's yellow, right? Blue in the movies because to mimic the flash of a lightning bolt, they use a xenon lamp. And xenon lamps give off a very bright, quick flash of light, but they give off blue light. It's not the right color of a lightning bolt. It's close to purple, but yeah, it's not exactly purple. Now, what I want to use this high voltage transformer for is to provide some energy for this little glass tube here. Now, this glass tube has a little weird looking point here. What they've done is this had a longer glass tube attached to it originally, and it was connected to a vacuum pump. So they sucked most of the air out of here, and then they heated up the tube to get it to melt and seal off the vacuum. So if I were to drop this thing, it would implode. It wouldn't explode. Because there's lower pressure inside, it would crush down, and then glass would go flying, but yes, it would initially implode. Now, it also has a piece of metal on this end and a piece of metal on this end, which you can't see because somebody puts the tape on it. There's a little rod with a disc on this end and a little rod of metal over here. And what I'm going to do is I'm going to put the high voltage transformer up to one end, hit the button, and
Magic.
Oh my god.
now, you guys want me to go again. However, if I ask Nicholas to face forward and hold that little button, this is a
There's a button. Nicholas.
ionizing radiation monitor. That little click was from one bit of ionizing radiation entering the detection chamber, creating a voltage inside of here, which it displays as a click. Okay. There's another one. There's another one. That's called background radiation. There's no way of escaping it. There's radioactive particles inside of our body that could be creating that click. There's cosmic rays coming from outer space that could be creating that click. There's radioactive materials in the Earth's crust that could be creating that click. Okay? Now, if you hold it, has a lot more clicks. That's because this device, using this very high voltage, produces X-rays. A lot of X-rays. So I'm actually going to ask you guys all to back up. Like, get up out of your seats and back up.
No problem.
All right, Rochelle's the first line of defense.
Yeah, but like it's conformity, so I gotta
No. Now, listen, the X-rays that this thing produces are not going to kill you.
Bet.
They're not even going to give you They're not even going to give you cancer in the amounts that I'm actually producing here, but just to be safe, just so you guys don't run home and say, Mr. Bull shot X-rays at
I'm
me.
probably gonna say that anyway.
How about you, Mr. Bull? Mr. Bull?
Yeah, I'm still standing here.
Mr.
Yeah, because you're way closer to death than we are.
That's right.
Yeah, you're older anyway.
Basically 1 foot in the grave. Anyway, and I got good insurance.
Okay.
I know.
This is called taking one for the team. Okay?
What about your Logan and Logan?
Yeah, what did Logan do?
Okay, so the interesting thing about this is when I produce this little green line, one interesting thing I can do with it is to take this magnet. Oh yes. All right, so I'm done with this thing. You guys can come and have a seat. again.
Mr. Bull, was this I want to be radiated.
This is too much for me.
Now that would make sense, yeah.
Now I'm going to stop using this very, very old cathode ray tube. I'm going to use its great grandbaby. Grandbaby, not grandma. This thing that was blocking Wynn's view.
Oh, I saw this before.
What is this?
TV.
It's a monitor.
It's a monitor. What? Guys,
Oh, sorry.
It's like a cathode ray one, right?
it's a CRT monitor, which stands for cathode ray tube monitor. This operates on the same principles as that thing over there. It has a high voltage transformer in the back that shoots a beam of cathode rays, not left to right like in that tube, but from back to front, and there are materials coated on the inside of this screen that are similar to what was coated on this piece of metal here. That when the cathode rays strike them, they glow. This thing only glows green. This thing has 3 different coatings on it. One that's green, one that's red, and one that's blue.
Oh, yes.
But you can do something similar if I put a magnet next to the screen.
I did not know that.
Oh yeah, it's our old TV, yeah.
I know.
Oh, that's what happens.
Whoa.
It's not magic.
It's magic.
It's not magic.
It's
It's
not
not
magic.
Now,
Wait, you broke it.
interestingly enough, yeah, it looks as though I broke it. Because these screens can become magnetized. So right now, the screen itself is magnetized and is affecting the path of those cathode rays. So instead of hitting the pixel that they're supposed to hit, they're deflected just like they were when the magnet was here. So they're being deflected and hitting a different pixel than they were supposed to. Which is what's creating this pattern. Right? Ooh, interesting. He's putting that thing in front. You're getting clicks, right? But does that mean that what your mom said, don't sit too close to the screen, it'll give you cancer?
Yeah. Yeah.
Well, to know for sure, we would have to measure this for about an hour to get a background reading. Then we'd have to put it next to this thing to see if we get a higher reading when we are in front of the screen. Okay. It turns out that the reason these things are so heavy is because the glass that they use in here is leaded glass.
Oh, that's fine.
To absorb the x-rays. Because it does produce x-rays in here, but the leaded glass absorbs those x-rays, hopefully keeps them from... Now, these things usually when you turn them off and turn them back on, they have a de-Gauss function, which means to demagnetize them. Gauss was a guy that studied magnetism, and now it's back to normal.
Oh!
You got a good one? Oh, nice!
Oh, a magnet.
We've got some very strong magnets, neodymium magnets. Put that bad boy up there.
Don't die.
Elaine, do you remember magnets?
Nothing happened. Yeah, they're all cancer.
Those are individually weak. I thought they were the neodymium ones.
Oh, we got a weak magnet over here. Just trust us, it's a magnet. Trust us. Trust us. Trust us.
Where'd you get this?
Right here.
It's
been
been
right
on the
here
desk
like the whole
since day
year.
one.
Yeah, see?
Yeah, it is a magnet. That is something that's supposed to be on one of our little stirrers. Now give that to me so I can find what stirrer is missing.
No!
You should have given it to him.
No!
Mistake.
We were gonna put it in the electron. Yeah, we were gonna put it in the electron.
Yeah,
Well, it
that's
was on my desk. Everything's
Okay.
on my desk.
So-
Oh my
Wait, are you checking the
Exactly, right?
the monitor with the lead for science
Honestly.
of love?
The 6th grade.
Yes.
It's good.
What?
Don't worry, the lead's not going to get in.
It's gonna
Okay.
kill us.
So
That's dead.
The pudding model.
this device was actually used to overturn parts of Dalton's model, specifically the one that said that atoms cannot be subdivided. J.J. Thomson is given credit for coming up with the next model of the atom. We call it the plum pudding model.
Oh, yeah.
What J.J. Thomson said, well, let's just talk about what he did first. What he did, where's my remote?
Oh, over here. No,
I'll take it. What he did was to measure these cathode rays. He was one of the first people that actually measured the cathode rays in an interesting way. People had built these things as sort of like a curiosity, you know, just like, oh, this is cool. But he was one of the first to really systematically study it.
why it's wrong.
And so I have his paper, or a copy of it, from 1897 on the nature of cathode rays. And he's saying, we're doing these experiments to get some information as to the nature of cathode rays. Okay? So some people were saying, at the time, he talks about, well, here's what German physicists think it is. German physicists thought that it was something like light. We're producing some sort of waves in the ether, which is a sort of an archaic idea in itself. But sort of producing some sort of waves that are hitting that little screen and causing the flashes. Okay. Other people are saying that maybe they are actually material. So maybe something is inside of here that's being accelerated from one side of the tube to the other, and when that accelerated particle hits this little screen, that's what's causing the flash. So he's trying to figure out, okay, what is this stuff? So he he actually builds a couple of very interesting cathode ray tubes that have different features here. This one looks nothing like mine, but it's got an electrometer on it. He built one. This is kind of the really interesting one that I wanted to point out. He built a cathode ray tube that has a little electric plate in it. So it'd almost be like mine if I had two little plates here and I could hook it up to a battery and produce an electric field inside of here. So these cathode rays would be produced, they would travel through here, and then you would set up some sort of voltage on these plates, and what happens when a charged particle encounters an electric field? It either attracts or repels.
Which is
right?
a capacitor?
Sort of like a capacitor. Yeah. And so what he would see is that the path would bend. Remember we talked about photoelectron spectroscopy?
Yeah.
And we were sending those photoelectrons, those charged electrons, into an electric field and curving their path to get an idea of their kinetic energy. So obviously photoelectron spectroscopy came way after the discovery of the electron, which is what we're talking about right now. So what he did was he put that charged plate and he measured the deflection of those cathode rays. Sort of like what I did with the magnet, but he could control how big the electric field was so he could get some more quantitative measurements with this setup right here. And the first thing he did was he tried to disprove, or prove I guess, whether it was the gas that was inside. People said, you're just accelerating the gas inside of the tube from one side to the other. You're giving it a charge and then shooting it across the tube. That's what's hitting the screen and making this thing light up. So he said, well, if that's the case, different gases should produce different results in my device. So he measured a bunch of different gases. He put air inside of the tube, and then he sucked out most of the air. He put hydrogen inside, flushed the whole thing with hydrogen, and sucked it out so that the only gas remaining would be hydrogen. He did the same thing with what he called carbonic acid, which we call carbon dioxide. And the interesting thing that he's really trying to measure here is the ratio of the mass to charge. So it says M divided by E here. The ratio of the mass to charge. He can't directly measure the mass or the charge independently of each other. All he can measure is what the ratio of the mass to charge is. Okay, but what he found was that basically any gas produced, with keeping in mind experimental error, any gas produced the exact same ratio of mass to charge, which wouldn't make sense. Carbon dioxide weighs a lot more than hydrogen gas, so if it's the carbon dioxide or the hydrogen that's flying through the tube, we should get very different values of this mass to charge ratio, right? But he got the same ratio, okay? So it's not the gas. So people said, well, maybe it's the metal inside of here. You're breaking off little bits of this metal electrode, this cathode, and that little bit of atoms, charged atoms, are flying through and hitting the screen and causing it to light up. So he actually did the experiment again, but he tried different metals in there. He tried aluminum, he tried lead, silver, and he found that it didn't matter what metal was in there, he still got that same ratio of mass to charge. So he had to say, well, if it doesn't matter what gas is in here, I get the same types of cathode rays being produced. It doesn't matter what metal I use at the cathode to produce those rays, I still get the same ratio of mass to charge. And in fact, this ratio of mass to charge was a lot smaller than any element that could be measured at the time. So there was other ways of measuring mass to charge for actual atoms, in electrolysis and experiments like that. He found that these cathode rays were smaller than any element known. So the ratio is smaller than any element known, and it doesn't matter what you make the cathode ray tube out of, you get the same ratio. Well, what conclusion can you make? Well, so this is where he says the carriers of electricity in cathode rays, the mass to charge is very small compared to its value in electrolysis. The smallness of the mass to charge may be due to the smallness of M or the largeness of E or a combination of both. So he said maybe their charge is really large and their mass is really, really small. Okay? So basically what conclusion he makes is that these things, these cathode rays, are smaller than atoms, and every atom I put in there has those same little particles in them. So he was the one who discovered that atoms could be subdivided into smaller parts. What did he call those smaller parts? No, electron wasn't come up with for a long time after. He called them corpuscles.
Oh yeah, that's the first.
His corpuscular theory.
That's the two.
Well, corpuscles, what does corpse mean? Body, little bodies. Corpuscles. Okay. He didn't know what they were, he just knew that all atoms that he made his cathode ray tubes out of could produce these little bodies of negative charge. Now we call them electrons. Okay? Now he also knew that most atoms do not have an overall charge. So if all these atoms have little negative bits in them, there's got to be some positive in the atom as well. He didn't know anything about that positive charge. He said, well, okay, I guess those little negative bits are just in some sphere of positive charge. That's where we come up with this picture we call the plum pudding model. You guys are not British. I'm going to assume the majority of you are not British, so you've never had plum pudding before, right? You have? Delicious?
I don't like it.
No? What is it?
It's like raisins and stuff. Like, it was a long time ago, but I just remember not.
I know that.
Okay. So plum pudding, basically, for you guys, you can think of it like the raisin oatmeal. Relax. You don't have to eat it, you just have to conceptualize raisin oatmeal. Okay? So the raisins, or a chocolate chip cookie, fine. Yeah, those are delicious. Okay, so a chocolate chip cookie model, the little chocolate chips would be these little negative electrons, right? But they are surrounded by the rest of the cookie. So we got the positively charged cookie and the little negatively charged chocolate chips. Okay, that's just the conception that we're trying to make. Really, cookies are flat, atoms are spherical, so it would be the chocolate chip cookie dough ball.
Cookie dough bites.
Cookie dough bites. Okay. All right. So this was 1897. Again, the cathode ray tube experiments, the ratio of mass to charge, is the evidence that there are little bits of matter that make up all the atoms. Okay? But that's about all he could say. Now, J.J. Thomson, that's not all he did for us.
Wait, mass to what ratio?
Mass to charge. Yeah, it's a big plus sign because he knew there had to be positive charge. He just didn't know anything about it. So he said, well, I mean, I can't get the positive charge to jump out. Maybe it's this big sort of swarm of positive charge that all these little negative charges live in. Osama, something to add?
What?
Something to add?
If you would like me to.
Well, I'd like you to, if you have something important to add it. Otherwise.
I said you could think of it like a mama charge with all her little things.
That was important.
Thank you. Maybe if you're talking about the octomom before she gave birth, yes, you have 8 little babies surrounded by the mother.
She's flooring. Like fairy
That's not what I was
godmother, the
thinking
attic
for you.
flooring.
I'm not interested in that. Okay, here he is. Yeah! That guy. Total stud.
He looks like Watson.
A little bit. J.J. Thomson.
Wait, are his lenses uneven? No,
Okay. No, J.J. Thomson, oh man, Dalton must have been watching. Dalton's dead by the time. What happened was, if Dalton was alive, him and Thomson would have been like in so many fistfights because not only did Thomson, with the cathode ray tube experiment, overturn the idea that atoms could not be broken into smaller bits, he also overturned the idea that all atoms had the same mass. We were talking about isotopes, and Michelle, saying, of course we know about isotopes, right?
Yeah.
Everybody know that.
Yeah.
I said,
Why?
prove it.
I don't know.
Radiation. And Michael said, well, I know there's this carbon dating stuff that relies on the fact that there are different isotopes, so, you know, maybe. Okay, still not proving it. Okay, how does that work? J.J. Thomson actually discovered the idea of isotopes using the same type of device we have here, using a sort of cathode ray tube. All right, this is the picture that proves that isotopes exist. Say what?
Isotopes are real.
I could do that.
Nothing.
Oh, I get it.
I
I get it.
Okay, so what he's doing here is, instead of having just a phosphorescent screen that just glows when these cathode rays hit it, he's got a photographic plate here. Okay, so the beam is sort of coming in this way, and so it's almost like he put a photographic plate on the edge of this. Okay, but then what he did was he had that same sort of electric field in there so that the cathode rays would be deflected by that field. And what he's doing here is he's saying, well, I've got a bunch of different streaks corresponding to different curvatures. And so he's trying to assign each of these different curves to a particular thing that he knew was in his little cathode ray tube. So apparently he knew there was mercury in here, but he saw two different little lines here. And he assigned that to mercury with two different charges, mercury +1 and mercury +2. Because an atom that has a bigger charge is going to curve by a larger amount than the atom with a smaller charge. Right? Coulomb's law says the bigger the charge, the more the force, right? So a +2 is going to curve more than a +1. Okay? But what also affects the curvature is the mass. So mercury is pretty heavy, so it's got a lot of momentum, it doesn't curve that much. CO2 is lighter, and so it's going to curve more. So he's assigning this to CO2+. Okay, but the interesting thing is what's down here. There's two little spikes down here that he assigns to neon. But those peaks are so close together, finish my thought. He assigns these two different peaks as actually two different types of neon. He's saying not all neon is alike, because if it was, I would only see one peak here. I'm seeing two peaks at slightly different distances, so they must have slightly different masses. It doesn't have a very huge difference in the mass, otherwise I would see a much bigger separation. It's not twice the charge of one, otherwise I would see a much bigger separation. It's just a slightly different mass. And the explanation is that we have two different types of neon. So I'll show you how this works after break.